Okay. Start my share screen. Okay, and I think that we can start. So we're continuing the introduction to key elements required to understand machine learning. And probably some of them are known to some of you, but I hope you have found last week and this week several things which are new, interesting, or from a different perspective in order to better understand machine learning. So last week we stopped at discussing elements about statistics and probability. And the last thing that we have seen, we said that, of course, we need to understand several probability distributions, and the most important one was the Gaussian distribution. And actually, on these three slides is where we stopped last week. So we have the Gaussian distribution, also called the normal distribution, distribution from the exponential family. So we have a normalizing constant in front, and then e pow something. Yeah, actually we have seen that for this distribution we have the mode. It's unimodal. It means it has only one maximum, and the mode is centered on the mean, and also the variance sigma controls like how much we allow the distribution to be very centered and specific to the mean, or to be more spread on the x-axis, to be close to uniform if you want. So a more narrow distribution or not. And we have seen like the expectation of the Gaussian, it's actually the mean. This is an important property. So if we would pick only one point to describe the Gaussian distribution, we would pick the mean. If we have like 2 points, usually we pick the expectation, the mean, and the variance. And we see that the variance is sigma power2. So it's a standard deviation power2. And I guess that you knew all these things, and the last thing we have seen is that actually Gaussians can also be defined in a multi-dimensional space. So here is a two-dimensional Gaussian distribution. Actually, it's the same distribution, but now we have a vector of means, if you want. So this is a vector of means and a covariance matrix. And for example, here the vector of means had two components. It had like mu1 and mu2. And the covariance tells us which is the variance on each specific axis. So each multivariate Gaussian has k axes, depending on where k is the number of dimensions. In our case, it has 2 axes. And also the covariance matrix also tells us how these axes are different from the axes of the coordinate system that we are using, because you see like they are skewed. They are not always parallel to the coordinate system. So this is a covariance matrix. Otherwise, it's the same. Here we still have like x minus mu minus the mean pow2. But because we are using algebraic notation, x minus mu pow2 is now x minus mu transpose multiplied with x minus mu. So we need to work with algebraic notation. Cool. And now we would like to see the link between like the Gaussian distribution and the error for the regression that we have seen last week. And in order to do this, first we would like to see what happens if we sample points from the same Gaussian distribution. So let's assume we have the same distribution and we sample several points independently from the distribution. These data points, they are called IID, so they are independent because each sample is independent from all the other ones, but they are identically distributed because they are sampled from the same distribution. In our case, from the same Gaussian distribution. Yeah, just to remember, so probability of x and y is equal to the probability of x and probability of y if two random variables are independent. In our case, sampling the points, like the points are independent, therefore the probabilities, the joint probability would be the product of the individual probabilities. And now we say, okay, let's consider we have a sample of n points, so a larger number of points over a univariate Gaussian distribution. So we are in the case, a simple case with a scalar variable distribution, and all the samples are independent, but they are sampled from the same Gaussian. And this is like a representation. We have the underlying Gaussian distribution, and these are the points. So actually, we don't have the Gaussian per se, we just have the points. So we know that we have sampled x1, x2, xn, and of course the last point would be x uppercase n. So these are the endpoints. And we would like to estimate the most probable, yes, the best fit Gaussian distributions that got us these points. And actually, the red curve is this Gaussian distribution, the best fitting one for this set of points. It's not the real one; it's the one that will get us the best fit. And how do you compute this distribution? We start from the joint distribution. So here we have x, it's an array. Therefore, it means that here we have an array. It's x1, x2, and so on up till the last one. So it's an array with all these points. So the joint probability of all the points, given the fact that they are sampled from the same distribution, therefore they are governed by the same mean and the same variance. And now we use a fact. So this is here we use that they are identically distributed, and here we use the fact that they are independent. So because they are independent, actually this joint probability transforms into a product of individual probabilities. And each probability is a probability of the point being sampled from the Gaussian distribution. So we have the Gaussian distribution of sampling that specific point. Cool. And now we would like to maximize this probability. So this is called maximum likelihood. So this is the likelihood function. So how likely is it for a Gaussian distribution to generate this data? And we are maximizing this function. Of course, we'll be also maximizing what we have on the right. So we need to maximize the product on the right. Which is the simplest way of doing it? So we want to compute these parameters mu and sigma, in order to maximize this product. And probably you already know it's called maximum log likelihood. So we don't maximize this function. It's a monotonical function. Therefore, we can maximize the log likelihood. So if we maximize this function, or if we maximize the log likelihood, it's exactly the same. So we put a logarithm in front of the product. And now, of course, logarithm of a product is going to be transformed into a sum of logarithms. And if we have a sum of logarithms, so the logarithm of a product is transformed into a sum of logarithms. So we'll have something like, let's go to EndNote. Maximum log likelihood. We maximize the logarithm of the product is n from 1 to upper n out of the normal distribution of generating each point from the same Gaussian. with the same parameters. And now, like the logarithm is applied on a product, therefore we will have like it's a maximum out of a sum. So log of a product is a sum of logarithm of log of n of xn given by mu and sigma. And now actually so one reason we use log likelihood is the fact that usually we have a log out of a product because we will use the fact that the samples are independent. But the next, so this is one very good thing. But the next very good thing is the fact that actually most of the distributions that we'll be using are from the exponential family. And because they are from the exponential family, right now the logarithm actually is applied on an e power something, which is actually a very good thing. So what we have here it's something like logarithm of 1 over square root of 2p sigma power 2 e minus 1 to sigma power 2 x n minus mu power 2. So this is actually how it looks like. So again, we have a logarithm out of the product. So it will go into a sum of logarithms. So it will be something like logarithm out of 2 sigma 2p sigma power 2 under the square root plus a logarithm out of e power something. And here it's a nice, so logarithm out of e power something, actually this goes away and we'll already get this power something in front. Cool. So this is these are the two nice things why we use log likelihood in machine learning, and actually that the power of the exponent it's actually this term in the log likelihood. So you can see it's actually minus 1 over 2 sigma power 2. And now we need to sum over all the points. So we sum over all xn minus mu because we need to do it over all the n points. So that was only for 1 point, but we need to sum over all the n points. And then we get these terms which are still a product, and we'll get something like this. So minus n divided by 2 logarithm of sigma power 2 and so on and so forth. And what we need to do next, we need to maximize this function. In order to maximize this function, we need to compute the derivative with respect to the two parameters. So we need to compute the derivative of the likelihood with respect to mu. And after computing it, we will get to the fact, like if you want to do it as an exercise, it's pretty simple. Therefore, so this one goes away, it doesn't contain mu, this one goes away, this is very simple, xn minus mu power 2, 2 goes in front, and so on and so forth. So actually, we'll get the fact that the mean under maximum likelihood treatment, it's actually the mean of the n points. So we sum all the points from x1 to xn, and we divide by the number of points. So it's actually the average value of the point. And sigma, the variance, sigma power 2, the variance under the maximum likelihood treatment, it's actually the standard deviation power 2. So it's actually the variance in the data. So we have the error, the difference between each point and the mean, power 2 divided by the number of points. Cool, and this is a very interesting result because actually the expected value of the mean under maximum likelihood, it's actually the same value that we will get for the mean under the conventional statistics that we know. But actually, the variance under maximum likelihood is biased. So usually, in statistics, the variance is not 1 divided by n, it's 1 divided by n minus 1. So we actually get a biased variance. The real variance is actually n divided by n minus 1 multiplied with a variance computed by maximum likelihood. So actually, you can look at it this way. If n is equal to 2, so if we only have 2 points, the real variance should be 2 times larger than the variance under maximum likelihood. Cool. So here is a graphic, if you want. If we only have 2 points, the mean is correct. Always the mean is correct. But actually, what happens? The variance is 2 times more narrow. So with the green, here we have the real Gaussian, and with the red, we have the maximum likelihood Gaussian computed using this treatment, with only 2 points, because it's n equal to 2. So as you can see, the maximum likelihood Gaussian is narrower. If you want, it overfits. You have a bias. You have a very strong bias to the data that you have seen. Does this make sense? So you understand what happens in maximum likelihood, even for this simple case of a Gaussian. So actually, it's a very simple example of a bias to the data, of overfitting. So if we only have 2 points in statistics, we should have computed this green Gaussian, but the maximum likelihood treatment computes the red Gaussian, which is more narrow and more fit on the data. So it doesn't have the same variability, if you want. It's very precise, it's very narrow. Cool, and this is like bias. It's an important term in machine learning and in AI in general. So it's a term in order to describe a preference towards a particular perspective or result. And in our case, is bias of the estimator is the difference between the expectation of the estimator and the real value, the expectation or variance, like the parameters of the estimator, and the real expectation or real variance of the data that we have. And usually bias is related to overfitting. So if you hear about, we have a gender bias in NLP models, like in transformer models, like gender bias means that if you have male terms, usually it's a doctor. If you have women terms, usually it's a nurse. I had examples for the neural networks course this year with very interesting biases in transformers related to gender. So biases are everywhere in data, and they are captured by some of the models, and maximum likelihood captures these biases. Cool, and now let's go back to curve fitting, like to our regression. So in our regression model, actually what we will do, we'll say the following. So of course, we'll have like the curve that we want to compute, y of x and w. And for a given point x0, now what we'll do, we'll actually add a random Gaussian noise. So sorry, not random, like Gaussian noise. So instead of having only one point over here, which is a point y of x0 and w, we'll actually have now a Gaussian distribution. Like if you imagine the Gaussian distribution on the target axis, now of course you'll have a Gaussian distribution. This distribution is centered on this point, on the value of the function. But we have some noise. So it's a Gaussian noise, the noise which is inherent in any data. So now we'll have like, it will be a probability of the target given x0, because of course this point influences influences y, the predictive function. Given x0, w is the weights, and beta, and actually beta is called precision. So beta would be how precise is our Gaussian function. If you want, beta is 1 over the variance, and it's called precision. How precise is the Gaussian distribution? If it's very precise, the variance is close to 0. Yeah, it's like a Dirac impulse. If the precision is very small, then it's like a uniform distribution. The variance is very high. Yeah. So beta called the precision, it's 1 over the variance. And you can see right now, this probability can be described as being, so it's a probability of the target, because the target is a Gaussian distribution. The mean of each Gaussian is a value of the predictor function, y in this point x0 and w, because like we have a regressor function. And beta minus 1 will be the variance right now. And now we say, okay, we need to compute the best value for the predictive function, given that we have a set of n samples which are independent, but they are sampled from the same noise, from the same Gaussian noise for each point y. So for each point y, we'll have the same Gaussian noise. And actually, we're going to use the same treatment. We're going to talk more about this next week when we discuss the linear model for regression. Right now it's just an introduction in order to see what happens. So we need to compute maximum likelihood in this case. So we have a probability over the targets given the training set, the weights that we need to compute, and how precise we'd like the noise function to be. And actually what happens after we compute again, we'll compute the log likelihood similar to what we have done previously. And actually we'll get to a formula like this. We won't go very much into it, but what's important to see, actually the log likelihood here has this term, and this is the most important term. Actually this term is beta multiplied with the error, the sum of squares error, now because this is the sum of squares error that we have discussed. The error in the data, yeah, because it's error in the data. Cool. So actually, if you want, in order to maximize, so if we want to maximize the log likelihood, what we need to do, because here we have a minus, we need to minimize the error. So actually, maximizing log likelihood in this case, it's exactly the same as minimizing the error. So the two views are exactly the same. So we have reached the fact that we wanted to minimize the error. This is done by maximizing the log likelihood under a Gaussian noise. So if we add Gaussian noise, we go exactly to what we have talked about, minimizing the error. So now we have a justification why we want to minimize this error. We minimize this error because this error is considered as being the error that we get under a Gaussian noise for all the points in the data set. And after we determine W, this is called the W maximum likelihood. So the weights under the maximum likelihood treatment, we can also compute the precision. We'll talk about next week more about this. And now this is called predictive distribution. So the predictive distribution, right now it's a function, it's a Gaussian function if you want, and we'll have the most probable value will be given by y of x and W maximum likelihood. And this is here the red curve. And in pink, if you want, we have the predictive distribution affected by noise. Yeah, so this is plus minus 1 standard deviation in pink. But usually we're gonna just use this function. So the function that we have over here, the regressor function. But actually, we can also have an estimation of the noise, how much noise we have in the training data. So we can also compute the noise. The noise in the training data is given by beta. This is where we stop. So it's very nice that we can use maximum likelihood, but we have seen that maximum likelihood has a bias, is prone to overfitting. And we already know that if we use the sum of squares error function, we can overfit. And we have seen that in order not to overfit, we can add regularization. And actually, maximum a posteriori is a step towards base. So maximum a posteriori says, let's put a prior, so this is called a prior. Let's put a prior Gaussian distribution over the weights. So you see now the weights, they are not only 1 point, they are like a prior distribution. This is a very simple Gaussian multivariate distribution, and we'll see how we can interpret it. And now we're going to use Bayes theorem. And Bayes theorem says if this is a prior that we get, the posterior distribution after we see the training set, it's actually given by the likelihood multiplied with the prior. And actually what we get when we maximize, so when we maximize this posterior distribution, so this is base theorem, we get the posterior distribution for W. And when we maximize this posterior distribution, we'll get the fact that the new error that we minimize, it's actually this one. Can you tell me what we have over here? Actually, over here, we have the error in the data that we had in the maximum. So it's the same as for maximum likelihood plus the regularization coefficient, if you want. So actually, if we use maximum a posteriori gives us the regularization part from a mathematical point of view. So we have not added regularization just because we wanted to add regularization. Actually, regularization is given by the maximum a posteriori treatment. And we finish like, this is like the posterior value for the weights. But actually what we are interested in is the predictive value of the target. So we are actually interested which is the probability of a target for a new point x given the training set. So this is a training set and we want to make a prediction for a new point x, scalar x. And actually, in order to do this, we need to integrate over, like we need to use a product rule and we need to multiply the probability of the target with the posterior of the weights. So this is a posterior that we have just seen. And the interesting thing is that we get to a Gaussian distribution, and this Gaussian distribution has some parameters that we're going to expand. But actually, we get to a Gaussian distribution over the target, and it's going to look like this if you want. So right now, we're going to have for each point, for each x that we have over here, we're going to have a mean value of x and a variance for this point. Like this is the end of the first part of the introduction, and from here on, Costin is gonna continue.
Hello, Tran. Should you stop presenting?
This is what I'm doing. I'm stopping my sharing. I'm also closing my camera now too. You can start sharing.
1 second. I'll share this in a second. Can you see the slides?
Yes.
Okay. Great. So Tran told you about the polynomial curve fitting. Ryan, are you still here?
Yes.
Do you think I should go through the reminder?
No, I think that everyone is okay.
Okay, so the problem is that you've seen these slides about regularization and stuff, and the problem is related to the model selection, meaning that we need to identify the hyperparameters of the model, the value of m and the value of lambda to establish the regularization and the importance of regularization, and also what is the complexity of the model by deciding this value of m. and this. Okay. Now, in order to identify these two values, we need to go through a couple of steps. If we have enough data, some of the data will go to the training in order to establish the value of m and lambda. Then we'll have to put aside some data as validation in order to validate the values that we identified during training. And finally, some parts are kept outside of the combination of training and validation as a test set, where this data is not seen during the training or the validation, and it's used only to establish the final quality of our model. However, most of the time in real situation, we have limited data. And therefore, we cannot allow ourselves the luxury of having both training and validation data sets. And therefore, we will wish to use most of the data for the training part. Therefore, the validation will be either small or inexistent. And therefore, we will have noisy estimation of predictive performance. And that's a problem. How can we solve this problem? Well, one way of solving the problem is deciding to employ cross-validation. What is this cross-validation? Do you know? Have you heard of cross-validation?
Yeah.
Okay, so we divide the data into S sub-data, and we keep aside each time at each run a subset for testing, and we train on the other subsets. That involves a couple of problems. The first problem is that if we divide the data in S sub-data, then it means that the number of runs is increased by a factor of S, because we'll have to do a run for the first subset, another run for the second subset, and so on, until we get to the final subset. So instead of doing only one training, we will have to do S such trains in order to employ cross-validation. This is an issue, especially if the model is complex. It will take a lot of time and resources to develop this. However, this is not the biggest issue that we might face during cross-validation. You know, at the end of cross-validation, we would like to have a model that can be put in production, so that it can be further used as the model for estimating different things from now on. But if we use cross-validation, it means that we're training several such models, not only one model. We'll have one model here, another model here, and so on. And those models might have different parameters. And now the issue is, I only want one model. How can I combine all these models that I'm getting by training them on different parts of the data? And how can I remain with only one model that will be the best? So this is a real problem that there are some issues, some methods of solving this issue, but they are depending on the problem and on the data set and so on. So this is a problem. How can I identify correctly the parameters that should be used further? If the number of partitions that I'm using, the subsets, subdatas, is equal to the number of training instances, then the model is the method, instead of cross-validation, is leave one out. This is the name given to cross-validation. Am I clear? Is it something that you didn't understand so far? All good? Are you still hearing me?
Yes.
Okay, thank you. Another problem. So this is one of the problems that we might face. Another problem is called curse of dimensionality, and it's given by the fact that most of the time the problems will have multiple dimensions, and we will not be able to use all these dimensions. For example, in this picture, we have a data set having 12 dimension in 12 axes of variability, out of which only two such axes are presented, the 7th and the 6th axis, in order to plot some data that we have. So only 2 out of 12 dimensions are seen in this picture. There is a combination of materials, each color representing a different type of material. Now the problem is we have this point, and the issue is, how can I evaluate correctly this point? What should I do? What color should be this cross colored to? Blue, green, or red? What do you think? And why?
Either green or red.
Why? How did you decide that it should be either green or red? Why not blue? Because this is what you removed from.
I guess it's because of clusterization.
Clustering is called. Okay. So basically what you're saying is that you're clustering the points that are in this figure, and you say that the closest points to the cross would be red or green, or the cluster that the cross should be part of should be either red or green, right?
Yes.
Any other opinions? Okay. If not, yeah, say, please.
I think we cannot make a good classification because we don't know how the points relate on the other dimensions, on the other axis.
Okay, it is very true. So both of you had good reasoning, and now I will try to present these two together. So first of all, we can split the whole space that we have in this picture in the different areas, and we could take the majority of points from that area as deciding the color of the sub areas. For example, on the top row, we have mostly blue samples, and therefore all the sub areas of the first row should be blue. And then, based on the majority of points in each sub areas, we will color the sub areas in that color. However, so this is what the first answer was about. Now, the problem is that there are some areas where we have very few points. And therefore, we don't know exactly what's going on there because we don't have samples. We don't have training data for those areas. And the problem is especially in, for example, this part, where we have only 2 or maybe 3 points, but otherwise we have 10 dimensions that should be placed in here. So we're not very sure what's happening here. Okay, we have it's true that we have 3 points, but if we have another 10 dimensions that should be placed in this square, then those 3 points will not be enough. And this is related to what the second answer was about. And let's see, suppose that we have only one dimension, then we will have 3 subareas. If we have 2 dimensions, x1 and x2, then we will have 3 power 2, so 9 subareas. If we have 3 dimensions, then we will have 27 subareas and so on. If for the data set that I presented you earlier, we have to add another 10 dimensions, it means that we will need a number of training points that will be at least exponential in the number of dimensions. Because we will need at least 1 point in each such subspaces that is being created when adding all the dimensions. And most of the time we don't have the training data. I mean, we cannot find millions of data just to fill in at least 1 point in each such subspace. And then what can we do? So if we use this solution, we will need an exponential number of training data, exponentially in the number of dimensions. Now, if we go back to the curve fitting problem, we can see that we can tackle this problem. Let's suppose that we have m equal to 3. So we can write the value of y given x and the parameters w as being a bias w0 plus some combination of only 1 dimension at a time, and then combination of 2 dimensions at a time, and then combination of 3 dimensions at a time. And therefore, if we use such a representation, then we will need 1 parameter plus d square plus d to the third. So it means that in order to evaluate this, we will need a number of parameters, a number of training points at least, that is of the order of d to the m, where d is the number of dimension and m is the complexity of the model that we have chosen. It's better than before because now we have a power grow instead of an exponential, but still is way too much. So we will still face the issue of not having enough training data to fit correctly the curve. So what else can we use? There are 2 important properties that can be exploited. First of all is the fact that the real data is confined into a space having lower dimensionality. So if we consider a hypersphere of with a lot of dimensions, the real data will not be evenly distributed all over the sphere. The real data, it will be placed in some sub areas of this hypersphere or hypercube or whatever we decide to consider as our space, which means that the space that we are searching for, it's much smaller, and being much smaller, it means that we will need much fewer points for training. Moreover, another important thing is that the direction over which important variations in the target variables occur may also be confined. So even though the data has a lot of dimensions when it was collected, there is a high chance that not all of this data, all of the informations are useful. I mean, for example, we can evaluate, I don't know, the temperature in a house, and to consider what is the government at that moment. There are things that are not related, even though that we are collecting them and we use them in the data set. There might prove to be not directly, I don't know, involved in establishing the target. So therefore, if not all the dimensions that we are collecting are equally important, it means that we can restrict the data set that we are using and we are trying to feed to only those dimensions that are really important and will count when we are doing the regression of or classification that we are asked to. This is one property. Another property is that real data will typically exhibit some smoothness properties, at least locally, which means that if we have two points that are close to each other, their values, their targets, should also be close to each other. And therefore, we can use this property in order to interpolate some values that we don't have based on their neighbors or the values, the target values of their neighbors. Are there any questions so far? Okay.
In this category is also principal component analysis, or
PCA is in the first part. I mean,
yes, first part.
You may use PCA in order to identify the axes that are important for your data set, so that to choose what axes you should use further and what other axes you should discard. But yes, PCA is related to the fact that the data set will not be equally spread in all the directions. Any other questions, or should we move on? Okay. Now, we will work in this class with decision theory. First of all, we have to work with probability theory, which tells us how to deal with uncertainty. And then decision theory is combined with this probability theory in order to help us make the optimal decision when we have some uncertainty. In order to make these decisions, we have two steps. First step is the inference step, where we estimate either the probability of the target given the point, or the joint probability of the point and the target. And then we have the decision step, in which for a given X, we determine the optimal target. So if we know the point for which we need to establish the target, then based on these probabilities that we computed in the inference step, we can make the optimal decision in finding T. For example, if we have the problem of diagnosing cancer based on X-rays of patients, the input of the problem will be a vector of pixels intensities from the image, which we will denote as X, and the output, the target, is if the patient has cancer or not. It's a binary output. And therefore, in the inference step, we determine what is the probability that the patient has cancer or doesn't have cancer based on the image that we receive as input. And then in the decision step, we make the decision based on these two probabilities that we computed in the inference step. Now, in order to make this decision, we might be interested in several techniques One of them is saying that we should consider the minimum misclassification rate. For example, we might have, so since we are working with binary decisions, we might have two different probabilities distributions, one for each class. For example, let's suppose that we have class 1 and class 2, and that the distribution for class 1 is the one from the left, and the distribution for the class 2 is the one from the right. As you can see, there are some areas where the two distribution overlap, and this is something natural. I mean, in real world, you will see something like that. And the problem is how to assign each value of x, for example, how to assign this point or this point or this point to which class, class 1 or class 2, so that to make as few misclassification as possible. So to miss the fewest. Now, since we have only two classes, we will have to split this entire space into two areas, one corresponding to the first class and another one corresponding to the second class. So the space will be divided in decision regions, RK, and the boundary between them, is called decision surface or decision boundary. So the problem is where we place this decision boundary. For example, we have x hat. X hat is the boundary between the region corresponding to class 1, denoted by R1, and the region corresponding to class 2, denoted by R2. And there are some issues. For example, let's suppose that the boundary is here at x hat. Okay, this area belongs to the second region. Okay, but it will come from the first curve. So these points from here are not part of class 2, but are part of class 1 because they are extracted from the distribution of class 1. Then again, the green part, so this part, plus the red part should not be placed in the first region as it is part of the second distribution. So those points from the green and the red areas should be denoted as making part of class 2. And now the problem is, how can we balance these errors, the green, blue, and red errors, so that to minimize the sum of these errors? Because all of them are errors. The blue ones are points that are classified in the second class, but they are part of the first distribution. And the green and red ones are part of the second distribution, but are classified as being in the first region. As you can see, as we move x hat to the left or to the right, the areas green plus blue will remain constant. And this is basically the minimum misclassification that we can obtain. However, as we move for left or right x hat, the area of the red area will increase or diminish. If we set the decision boundary as at the point x0, we can see that the green plus blue area will be the same, but the red area will disappear. Make sense? So, in fact, what we are interested in is to find this point where the red area cancels out. And to do that, we can make the following observation. To the left of x0, we have the probability of X being in C1 being larger than the probability of X being in C2. To the right of X0, we have the opposite. As you can see from X0 on, the probability of X being part of C2 is larger than the probability of X being part of C1. And therefore, we can establish this boundary at the point where these two probabilities are equal, and then assign each point to the class that has a higher probability. Makes sense? Do you have questions? So, the probability of making a mistake is the probability of putting one point in class R1, but it being part of C2, plus the probability of a point being placed in the second region, but making part of the first class. So since we have continuous distribution, it means that we have integral of probability of X being part of C2 over the region R1, plus the probability of X being part of class C1 over the region R2. As I told you, as we vary X hat, blue plus green areas remain constant while the red varies, and the optimal choice of X is X0 where the curves cross, because here the red area disappears. And therefore the minimum misclassification rate decision rule assigns each value of X to the class having the higher posterior probability P of class given X, which involves that the joint probability, which is only P of class given X multiplied by P of X. This is from product rule and base rule. So these formulas I think you know already, which means that if we want to maximize this or we want to maximize this is the same, because probability of X will not change over time. So this is can be eliminated. Okay. Are there any questions? Okay. Minimum expected loss. There are some situations where we don't want to penalize the errors in the same way. For example, in this situation with evaluating patients who have or don't have cancer, will lead to different costs if one patient is healthy and is declared as having cancer, and it has to go through some other investigations before being proved that he was in fact healthy. And it's a different situation when a patient is declared as being healthy and some days after that he dies of cancer. So there are some situations where we would like to impose some different penalties for different kind of errors. And therefore, we might want to introduce either a loss or cost function that we would like to minimize during training, or a utility function that we would like to maximize during training. And for example, in our problem, this loss might look like a matrix, and therefore it's called loss matrix, where we have on one side the truth, and then on the other side the decision that is made by the system. And if the decision is the same as the truth, then we have zero penalty. However, if the decision is different than the truth, then we will have different values, different penalties for different kind of errors. For example, this is a false positive. So a patient that is healthy is considered as having cancer, and we have a lower penalty for that. And this is also called error, type 1 error. And there is a much higher cost for type 2 error, where we have a false negative. So if a new value x from the true class CK is assigned to a different class CJ, then we will add some loss denoted by LKJ, so true class given class, in the loss matrix. And now we have to minimize the loss function, but the problem is that this loss function depends on the true class, which we don't actually know. And therefore, what we would love to have is to minimize the average loss, which is a summation over all the classes, all the true classes, summation over all the decision classes, over all the boundary, all the surface decision surfaces, over the loss Kj multiplied by the probability of x being in class Ck. And in order to choose these regions, decision regions, then the regions are chosen as to minimize this value. Expected loss as being the summation over all the true classes of the loss of the point being in class K and being placed in class J, multiplied by the probability of CK given X. The thing is that you might see that there are some classification errors. Most of the time, these classification errors arise from the regions where the probability of X given, the joint probability of X and class have comparable values for multiple such classes. And therefore, when we are not so sure what should be the real class of that point, we might want to use this reject option, saying that, look, the probabilities in this area, in these areas are so similar that I'm not very sure what decision I should make. And therefore, I would like to avoid making any decision in this area so that to lower the error rate. I don't want to make a mistake, and therefore I would rather not make any decision at all. And for example, this is the situation here in this area, where the probabilities are similar, and therefore if the probabilities are in this area, then we will use the reject option and will not make any decision. But now there is another hyperparameter that we should identify, because if we set this theta as being equal to 1, it means that all examples are rejected, because no sample will have probability equal to 1 in reality. If we set theta as being lower than 1 over k, where k is the number of classes, it means that nothing will be rejected, because there will be classes, there will be at least one class that will have a probability that is higher than this value, and therefore we won't be able to reject anything. Any questions? Now, I told you that there are two steps, inference and decisions. And we have three different alternatives. First, and the most complex, to use generative models, which means that we will have to determine first probability of X given the class, or the joint probability of X and class. Based on this, we will derive probability of the class given X, and based on these values, we'll make the decision. The advantage is that if we use generative models, we will know probability of X and we can determine new data points. So we can extract new samples, but disadvantage is that there is a lot of computation and demands a lot of data, and there is the most complex method that can be imagined. Another alternative is called is to identify discriminative models, which means to determine directly the probability that we'll need to make the decision, probability of class given X. And this method has the advantage of being faster and less demanding in terms of resources or data. And finally, the easiest way and I don't know, the most frequently used is to solve both problems by learning a mapping, a function that maps the input directly into outputs, and is called a discriminant function. The advantage is that it's the simplest method, but it has the disadvantages of not having the probabilities. And from this disadvantage, it means that there are some drawbacks. And these drawbacks are presented in this slide. So why should we separate inference and decision? In other words, why we should not use discriminative functions? First reason is minimizing risk. I told you that we might have a loss matrix that is associated to the problem, and this loss matrix might change over time. For example, think of this COVID situation. There are some costs of one person getting a flu, for example, and there are different costs of catching COVID. And therefore, since we have to imply some losses on the costs that the medical system will have to use in order to evaluate the patients and to do whatever it makes sense in order to stop the disease, then these risks impose the fact that the cost will change over time. And if we have only one mapping from inputs to outputs, it means that this mapping will not work if the loss matrix changes. It means that we'll have to retrain to take again all the data and so on. The next problem, reject options. Since we don't have probabilities, we cannot see what are the areas where the probabilities are similar, and therefore we cannot use the reject option. Unbalanced class priors. Only 0.1% of population has cancer, which means that if we train the data set, if we use for training a data set that respects this probability of people having cancer, then if we classify all of us as being healthy, we will have 99.9% accuracy. And no model that we could train would do better than that. So the model, in fact, will not train at all, will not learn anything. In order to be able to make it learn, we will need balanced training data. But if we use balanced training data, then a lot of the percentage of the population that has cancer is considered to be much higher. And therefore, what we typically do is to use balanced training data, but then compensate this by altering the data with some prior probabilities, which is impossible to do if we use discriminative functions. And finally, the last problem is that if we separate inference and decision, we might combine models. For example, using divide et impera for complex application. For example, I'm using X-rays, and then I see that I'm not very sure whether the patient has cancer or not, and therefore I can also order some blood tests, or I don't know what tumoral markers can be collected. Make sense? Are you still with me?
Yes.
Yep.
Yes.
Okay. Can we go forward? Regression. So till now we talked about classification when we have to make a decision. Now we'll talk about regression. Regression means that we will have to put a real value, not a class. So again, we have inference and decision. We have to determine probability of x and t. And for a given x, to make the optimal prediction y of x for the target. Most of the time we will use a loss function, which since it's continue, it means that it's double integral of the loss between the target and the prediction y of x, multiplied by the joint probability of x and t, dx dt. And for regression, most of the time we are using what loss? Have you tried? Have you worked with that? Have you had any problem of regression that you worked on? If not, most of the time is use the squared loss function, which is defined as y of x minus t to the square. And to determine the value of y of x, which minimizes the error, you make the expected loss, which is integral of this based on the earlier formula, is the loss multiplied by the probability of x and t. Since we are interested in the value of y of x, we derive this formula by with respect to y of x, and we set the derivative to 0. And I'm putting here the calculation that will be done. So if we derive this with respect to y of x, it will be I don't know, u square that is derived. It will be equal to 2 multiplied by u multiplied by u derived. So it will be one of the integral disappear with t of x because y depends on x, and we will have a 2 in front. We will have this y of x minus t. Y of x minus t derived with respect to y of x, it's 1. So we will have the formula from here. 2 integral of y of x minus t multiplied by p of x and t dt equals to 0. We put the part with plus to the left and the part with minus to the right, and equal this y of x, p of x and t equal to integral of t multiplied by p of x and t dt. Then this doesn't depend on t, so it goes in front. Integral of p of x and t dt is equal to p of x. I hope that you know this formula, and from here we will divide. We will say that this part goes in here, so we divide both left and right sides by p of x, and it means that y of x will be integral of t p of x and t over p of x dt. These using product or whatever is t multiplied by p of t given x, and this is expectation of t given x. So y of x that minimizes the loss, it's the expectation of the target given x. Knowing this fact, we can do some artifices. I don't know how it's called in English. By adding and subtracting this value, and then we will replace this formula that we get in here, and we get expected loss that is defined like this for regression using square loss function as being made of two parts. This first part, y of x minus the expectation of t given x to the square, which cancels out when y of x equals to this expectation, plus the second part of the formula, which is this integral. And in the next slides, I just showed how this can be rewritten. So first we start with this, and we see that since we have double integral, this doesn't depend on t, and therefore we can change the order here and put dt dx. This goes in front of the integral with t because it doesn't depend on t, and this will be p of x, and therefore the double integral goes to this. For the second part, there is a bit more difficult explanation. It takes some time. So first of all, we get all the terms from here. So it's p of x and t, dx dt, and then we see what these terms goes to. These two terms cancels out, and then we will have this part goes in here, this part goes in here, and in here we have plus and some minus, and we go I think y of x and goes in here. And then on the next slides, these are the formulas that I'm using. So these are some prerequisites, and I'm doing the computation, and finally I get to this result that the second part is only the variation of t given x multiplied by p of x dx. So in other words, the expected loss will be integral of the predicted value y of x minus the expected value to the square. So this is the basically the error from training, and this is the variation of the data, variation of t given x p of x, and this is the noise basically that that is given by the training data and represents the minimum value of the loss function. So lower than this we cannot go. And if we optimize this such that y of x will be equal to expectation of t given x, then the expected loss will be minimum. Is it clear? I didn't go through all the computation from the previous slides. I just made this computation and put them in there. If you want to go through them, please do. I would rather tell you to try to solve them by hand yourself before going to the solution that I put in there. I put it just to show you how such computations are made, and I think it will help you to try to remake those steps. They look ugly, but they are not so difficult, in fact, especially if you can take a look at what I did in there. I try to put in there all the steps so that you won't have issues in following the computation. If you will have issues, write me a message on Teams and I'll try to go through them with you. Okay? The important part is on this slide, and it says what is the minimum value of the expected loss, and also when we can get this this lowest value of the loss. Now, again, there is the same discussion as for classification. We have generative and discriminative approaches. We have generative approach where first of all we model the probability of t and x as being p of x given t multiplied by p of t, and then with the help of the Bayes theorem, we get p of t given x as being p of x given t multiplied by p of t divided by p of x. We have discriminative approach where we model directly p of t given x, and we can find a regression function y of x that maps the input to outputs directly during training. But again, there are the same issues in separating inference and discrimination as I presented in classification. So if possible, try to at least do something like this. Try to avoid building a regression. Most of the time, it's much easier to build such regression, but you will have some issues afterwards in getting good results, good F scores. Entropy is a measure of uncertainty associated with a random variable. It came from the coding theory, or I don't know, the closest similarity for us, for computer scientists, is with the coding theory, where we have x discrete variable with 8 possible states, and the problem is how many bits we need to transmit the state of x, and therefore the entropy is minus integral of p of x log of p of x, because we have only a discrete number of states. If the variable x would have been continuous, then the summation would have been replaced by integral. If we have all states equally likely, then p of x is 1 over 8 and the entropy is 3 bits and is the highest. But if we have some other probabilities that are different and sum up to 1, then we can use different codes and the entropy will be smaller and will be equal to 2 bits in this situation. Do you remember where we did something similar to this? How can we identify this code? We've learned the method especially for this problem in at PA, algorithm design. Can you remember what was the method to generate these codes? Or how are these codes called? These are Huffman codes and are generated using a greedy method. However, the entropy, so this is the closest, I don't know, domain where entropy is used for us, for computer scientists. However, the entropy came from physics, and there was a problem of identifying in how many ways can n identical objects be allocated to m bins. And they defined first the multiplicity, which is n factorial over the product of ni factorial. And then the entropy was defined as being 1 over n logarithm of the multiplicity, which is close to the value minus summation of probability or multiplied by logarithm of probability, where pi is the limit when n tends to infinity of ni over n. So the probability of assigning an object to the ith bin. And again, entropy is maximized when p of I equals to 1 over m, where m is the number of bins. And we can see that if we have a distribution that is smoother, so we have similar probabilities of being in the same class, the entropy is much larger than when these probabilities are much more different. Any questions so far? Okay, then we'll continue. The Kullback-Leibler divergence. It's a measure of the dissimilarity between two distributions, P and Q, and is defined as minus integral of P of x logarithm of Q of x minus integral of P of x logarithm of P of x, which means minus integral of P of x logarithm of Q divided by P of x dx is always positive, is not symmetric. So Kullback-Leibler of P given P and Q is different than Kullback-Leibler of Q and P, and represents the minimum value of the average addition of information that has to be sent when encoding a message X having distribution P using a different distribution Q. So it tells you that when you are trying to so this distribution come from the comparison of this distributions comes from the need to see how close a model is to the real one. And in order to do that, what you'll have to do is to compare these two distributions. And Kullback-Leibler is one method of comparing these distributions, because it says, okay, what loss do I have if I'm using the distribution that the model has learned during training instead of the distribution that is the real one? Or how far is this distribution that my model learned from the real distribution? However, in order to do that, you need to know both the distributions that are compared, P and Q. And most of the time, you don't really know the real distribution. Mutual information. If we have two variables, x and y, so we can build a joint distribution P of x and y. If x and y are independent, it means that the probability of x and y will factorize, and it will be equal to P of x multiplied by P of y. And using Kullback-Leibler divergence, we can see how closely related are these two variables, x and y, using this mutual information denoted by I of x and y. And this is defined as Kullback-Leibler of the joint probability x and y compared to the product of the two individual probabilities P of x and P of y. So this is the real probability, and this is the probability as if x and y would be independent. And it will give you a value that can be written as I of x and y equals to entropy of x minus entropy of x given y, or as entropy of y minus entropy of y given x. And it means that is the reduction in uncertainty about x as a consequence of new observations y. This value is greater or equal to 0 and is 0 only if x and y are independent. And the reverse is also true. If x and y are independent, it means that their mutual information is 0. And here ends the first part of my presentation. We will also talk about some probability distribution next. But this was the first chapter, the introduction chapter, where we talked about a lot of introductory stuff that we will be needing in the next classes for SSL. Do you have any questions before going very, very fast through the different probability distributions that we'll be using? Okay, then I'll start with these probabilities. The role of distribution is to model the probability distribution P of x over random variable x defined given a finite set of observation x1 to xn. The problem is also known as density estimation, and there are two types of distributions, parametric or non-parametric. The parametric distributions are governed by a small number of adaptive parameters, and we have as examples binomial, multinomial, Gaussian, exponential, and so on. And for these distributions, we try to determine the hyperparameters based on these samples that we're having, x1 to xn. However, they are limited to the fact that they assume a specific functional form for the distribution. So we are biased if we consider that the distribution is Gaussian. We won't be able to change it afterwards if we realize that the distribution was in fact binomial or I don't know what. The non-parametric distributions have some parameters, but they control the model complexity and not the form of the distribution. The form of the distribution depends on the size of the data set. And as examples, we have histograms, nearest neighbors, and kernels. And now we will start with the parametric ones, binary variables. We have x as describing the outcome of a coin flipping, and the probability to get head is mu, probability to get tail is 1 minus mu. And in order to describe this random variable, we can use a Bernoulli distribution, which is mu to the x, 1 minus mu to the power 1 minus x. X can be either 0 or 1. If x is 0, it means that we have a tail. So this cancels out and it remains 1 minus mu. If x is 1, it means that we have a tail. So this term cancels out and we get only mu, which is exactly what we have in here. The expectation of this distribution is mu, and the variance is mu multiplied by 1 minus mu. If we have n coin flips, what is the probability of having m heads? Is denoted by probability of m heads given the fact that we have n flips and the coin has a mu probability of getting heads. Is modeled using binomial distribution, which is combination of n taken to the m, mu to the m, 1 minus mu to the n minus m. N is the number of coin flips, m is the number of heads that we would like to have. The expectation of the binomial is n multiplied by mu. So n multiplied by Bernoulli. The variance is again n multiplied by mu multiplied by 1 minus mu. So it's n times the variance of Bernoulli distribution. And for example, this is a plot where we have 10 flips and float coin that will have only 25% chances to get head. And this is the distribution of getting M heads. So since the coin is bad, the highest probability will be somewhere between 2 and 3. And as you can see here, the highest probability is to get 2 heads, and the next highest probability is to have 3 heads. Now, if we have discrete variable, it means that this variable can take one of k possible mutually exclusive states. And in order to represent such a variable, the easiest way is to use a vectorial representation having k dimensions, k values, in which one of the elements is 1 and the rest is 0. The value that is 1 corresponds to the state in which that point can be placed. So for example, if we have 6 possible states and the point is in state 3, it means that the point can be represented as 2 zeros, a 1 on the third position, and another 3 zeros. If we denote by mu k the probability that xk equals to 1, it means that the probability of x given mu can be represented as the product mu k to the xk, and is called generalized Bernoulli. Expectation of x given mu equals to mu. Mu this time is a vector having a number of components equal to the number of states, and the sum of all these probabilities will be equal to 1. If we have n observation, what is the probability of having m1, m2, mk observation in category 1 to k, where the summation of all mk equals to n? Well, we have a multinomial distribution that will be a combination of n taken to the m1, m2, mk, which is which has this definition, multiplied by the product of mu k to the mk. With the observation of mu k maximum likelihood, so mu k that maximizes the likelihood to be equal to the mk over n, so the number of points in class k divided by the total number of points. Gaussian distribution, I hope that you know best this distribution because we will work a lot with it. This is the Gaussian in 1 dimension and has this formula, and this is in multiple dimensions, and we will have a covariance matrix that we'll be using. It's basically the same formula, but is adapted to the fact that we don't have only 1 dimension, but we have multiple such dimensions. The Gaussian distribution has some issue. If we have outliers, then the Gaussian will try to cover for them. So we'll try to explain these outliers. So instead of being robust, for example, in the left picture, we have in green and in red the Gaussian and the t distribution, student t distribution, and we see that they kind of overlap. The only point where they don't overlap a bit is here at the top. But if we have some outliers, you can see that the Gaussian will distort, let's say, trying to explain these outliers as well. While the student t distribution will remain the same. Now we'll go to the non-parametric methods. Do you have any questions before we continue with these methods? Okay. Parametric distributions models are restricted to specific forms, which may not always be suitable because you don't actually know the distribution from which the samples were extracted. And as I told you, there might be issues if we model a distribution. If you try to fit a distribution a specific form, if the distribution of the training samples is different. In the same time, the non-parametric approaches will not make any assumptions about the shape of the distribution being modeled, but it has some other issues that I will present next. From this class, I told you that we have histograms, near neighbors, and kernels. The non-parametric models have the problem that they need to store and compute with the entire data set. So they will be quite slow because of that, as you always need to go through all the data set and make the computation. This involves also much more resources needed, not only time, but also computation power and space for the dataset. On the other hand, the parametric models, once fitted, are much more efficient in terms of storage and computation because you only need to save the hyperparameters and your set. For example, at the Gaussian, you only need to save the mean and the standard deviation, and that's it. Two values, and you're good to go. Or the means and the covariance metrics, and that's it. And in here we have k nearest neighbors for classification, and it's an explanation why it works. If we have a data set with nk data points from class ck, with the summation over all k's over all classes of nk equal to n, then we consider the probability of x being the number of points k from a volume around x multiplied by n. So k divided by n or multiplied by v. So if we have a neighborhood of a point x, we can compute the probability of x from there as being the number of points from this neighborhood divided by n multiplied by the volume, by the neighborhood volume. If we consider for this formula for each class, we have p of x given ck, it will be kk divided by nk multiplied by v. So the number of points from the volume that are part of class k divided by the number of points from any class that are that can be found in that volume. And since p of class is equal to nk divided by n, and using Bayes' theorem, it means that probability of class given x, it will be probability of x given class multiplied by probability of class divided by p of x. And if we consider the formula from here and here along with this one, the probability of ck given x, it will be kk over k. So the number of points from class k divided by the total number of points found in the vicinity of x, or in a volume that spreads with its origin x. And if k equal to 3, we have something like here. So the black point is evaluated as being red because its three closest neighbors will be 2 red and 1 blue. So the majority will be red. So it will be classified as a red dot. To the right, we have the same data set, but with the boundary representing by one nearest neighbor, so k equal to 1. We only consider the neighbor, the closest neighbor when we evaluate each dot, and you can see that this if we connect the closest points from different classes, the boundary will be exactly in the middle of these connections. And in here we have for some data set for a data set we have the distribution of classes given different values for k. So we have k equal to 1 in the left, k equal to 3 in the middle, and k equal to 31 to the left. As you can see, the value of k acts as a smoother, so the data will be, I don't know, it will look smoother. The boundaries will look smoother, and will have a larger number of errors when k increases, because we consider more such sorry, it's not correct. The areas will not be so broken. I don't know how to say. But since we consider more neighbors, we will have a higher confidence that the results are better and the error is lower. If n tends to infinity, it was proven that the error rate of the one nearest neighbor classifier is never more than twice the optimal error that is obtained from the true conditional class distribution. So this k nearest neighbors is not such a bad classifier, even though it is very simple. I mean, all you have to do is to compute what are the nearest neighbors for that point, for the point that you need to evaluate, and then take the majority class, and that's it. That ends my presentation. Thank you very much for listening to me. I hope that you understood what I was presenting. And if you have any questions, please tell so that we can talk about them. If there aren't questions, then thank you very much. Yes, Cesar, you want to say something?
Yeah. Can we combine, let's say, distributions and k-nearest neighbors, like Gaussian distribution and k-nearest neighbors, to, for example, give less importance to neighbors that are farther away?
That will be also a k-nearest neighbors without the Gaussian, but it will be weighted nearest neighbors, in the sense that exactly what you say, the farther away the points will be, the neighbors will be, the least influence they will have on the evaluated point. But it remains a k-nearest neighbor. It doesn't involve Gaussian. If you use this weighting, so you still take the most the closest neighbors, the classes of the closest neighbors in consideration, but you weight them by the inverse of the distance.
Okay.
And it remains k nearest neighbors, even though you add this parameter. It's not getting in from the non-parametric method class to the parametric method class. Maybe you can use this Gaussian in a different way, but it will stay in this class of non-parametric.
Understood. Thank you.
You're welcome. Any other questions? Any other problems? Okay, if not, then you will meet next week with Traian, and we'll meet together in 2 weeks from now at the next class. Thanks for listening, and thanks for being patient. I recommend you to do the computations from the slides with the squared laws to see that they will lead to those values that I put in there. It will help you when you'll prepare for the final exam. I know it's early for that, but just to know about it. Thank you and good night. Traian, do you want to add something or?
The last word you said. Thank you and good night. See you next week.
Okay. Bye-bye. Thank you.
Bye. Good night.
Bye. Thank
Bye-bye.
you. Bye bye.
Goodbye. Thank you. Bye bye.